Hello everyone, I am Vamshi. I am from ACE department. My topic is about Gaussian elimination method. In mathematics, Gaussian elimination, also known as row reduction, is an algorithm for solving systems for linear equations. It consists of a sequence of operations performed on the corresponding matrix of coefficients. This method can also be used to compute the rank of a matrix, the determinant of a square matrix, and the inverse of an invertible matrix. The method is named after Carl Friedrich Gauss. Although some special cases of the method, albeit presented without proof, were known to Chinese mathematicians as early as circa 179 CE. To perform row reduction on a matrix, one uses a sequence of elementary row operations to modify the matrix until the lower left-hand corner of the matrix is filled with zeros as much as possible. There are three types of elementary rows operations: swapping two rows, multiplying a row by a non-zero number, adding a multiple of one row to another row. Subtraction can be achieved by multiplying one row with one and adding the result to another row. Using these operations, a matrix can also be transformed into an upper triangle matrix, and in fact, one that is in row echelon form. Once all of the leading coefficients, the leftmost non-zero entry in each row, are 1, and every column containing a leading coefficient as zeros elsewhere, the matrix is said to be in reduced row echelon form. This final form is unique. In other words, it is independent of the sequence of row operations used. For example, in the following sequence of row operations, where two elementary operations on different rows are done at the first and third steps, the third and fourth matrix are the ones in row echelon form, and the final matrix is the unique reduced row echelon form. Using row operations to convert a matrix into reduced row echelon form is sometimes called Gauss-Jordan elimination. In this case, the term Gaussian elimination refers to the process until it has reached its upper triangular or unreduced row echelon form. For computational reasons, when solving systems of linear equations, it is sometimes preferable to stop row operations before the matrix is completely reduced. Definitions and examples of algorithm. The process of row reduction makes use of elementary row operations and can be divided into two parts. The first part, sometimes called forward elimination, reduces a given system to row echelon form, from which one can tell whether there are no solutions, a unique solution, or infinity many solutions. The second part, sometimes called back substitutions, continues to use row operations until the solution is found. In other words, it puts the matrix into reduced row echelon form. Another point of view, which turns out to be very useful to analyze the algorithm, is that row reduction produces a matrix decomposition of the original matrix. The elementary row operation may be viewed as the multiplication on the left of the original matrix by elementary matrices. Alternatively, a sequence of elementary operations that reduces a single row may be viewed as multiplication by a Frobenius matrix. The first part of the algorithm computes an LU decomposition, while the second part writes the original matrix as the product of a uniquely determined invertible matrix and a uniquely determined reduced row echelon matrix. Row operations. There are three types of elementary row operations which may be performed on the row of a matrix. Swap the position of two rows, multiply a row by non-zero scalar, add to one row a scalar multiple of another. If the matrix is associated to a system of linear equation, then these operations do not change the solution set. Therefore, if one's goal is to solve a system of linear equation, then using these row operations could make the problem easier. Echelon form. For each row in a matrix, if the row does not consist of only zeros, then the leftmost non-zero entry is called the leading coefficient of the row. So if two leading coefficients are in the same column, then a row operation of type 3 could be used to make one of those coefficients 0. Then by using the non now row swapping operations, one can always order the row so that for every non-zero row, the leading coefficient is to the right of the leading coefficient of the row above. If this is the case, then matrix is said to be row echelon form. So the lower part of the matrix contains only zeros and all of the zero rows are below the non-zero rows. The word echelon is used here because one can roughly think of the rows being ranked by their size, with the largest being at the top and the smallest being at the bottom. For example, the following matrix is row echelon form and its leading coefficient are shown in red. It is in echelon form because the 0 is at the bottom and the leading coefficient of the second row in the third column is to the right of the leading coefficient of the first row in the second column. A matrix is said to be in reduced row echelon form. Furthermore, all of the leading coefficients are equal to, which can be achieved by using the elementary row operation of type 2, and in every column containing a leading coefficient, all of the other entries in that column are 0, which can be achieved by using elementary row operation of type 3. Examples of the logarithm: suppose the goal is to finally describe a set of solution equations the following system of linear equations: 2x plus y minus z is equal to 8, minus x minus 5 plus 2x is equal to minus 11, minus 2x plus y plus 2z is equal to minus 3. Once y is also eliminated from the third row, the result is a system of linear equations in triangular form. And so the first part of the algorithm is complete. From a computational point of view, it is faster to solve the variables in reverse order, a process known as back substitution. One sees the solution is z is equal to minus 1, y is equal to 3, and x is equal to 2. So there is a unique solution to the original system of equations. Instead of stopping once the matrix is in echelon form, one could continue until the matrix is in reduced row echelon form, as it is done in the table. The process of row reducing until the matrix is reduced is sometimes referred to the Gauss-Jordan elimination, to distinguish it from stopping after reaching echelon form. The method of Gaussian elimination appears, albeit without proof, in the Chinese mathematical text. Chapter 8, Rectangular Arrays, of the 9th chapter on the mathematical art. Its use is illustrated in 18 problems with 2 of 5 equations. The first refers to the book by this title is dated to 179 AD, but parts of it were written as early as approximately 150 BC. It was commented on by Liu Hu in the 3rd century. The method in Europe stems from the notes of Isaac Newton. In 1670, he wrote that all the algebra books known to him lacked a lesson for solving simultaneously equations, which Newton then supplied. Cambridge University eventually published the notes as Arithmetic Universalities in 1707, long after Newton, Newton had left academic life. The notes were widely imitated, which made what is now called Gaussian elimination a standard lesson in algebra textbooks by the end of the 18th century. Carl Friedrich Gauss in 1810 devised a notation for symmetric elimination that was adopted in the 19th century by professional hand computers to solve the normal equation of least squares problems. The algorithm that is taught in high school was named for Gauss only in the 1950s as a result of confusion over the history of the subject. Some authors use the term Gaussian elimination to refer only to the procedure until the matrix is in echelon form, and use the term Gaussian elimination to refer the procedure which ends in reduced echelon form. The name is used because it is a variation of Gauss elimination as discovered by Wilhelm Jordan in 1888. However, the method also appears in an article by Classen published in the same year. Jordan and Classen probably discovered Gauss-Jordan elimination independently. Okay, thank you for giving this opportunity.